Well, good morning. This is unfortunately a little late getting started. 8:13 in the morning on Thursday, the 20th of July, 2017. Supposed to be Math 238, differential equations, and I'm the only one in the room. I'm hoping someone else will show up. I was here early thinking I was going to get a lot done before the class. Unfortunately, the fan room right next door, mechanical room just next door to us here, was making a whole lot of noise, and I went back to my office and called maintenance, and it rolled over to the Birmingham campus, but still nobody picked up the phone there. So I called the HVAC technician here. It immediately went to voicemail, and then I went to the front desk to see if they had a way to get in touch with anybody. Happened to see a maintenance person at the front desk and told them about it. He came with me up here and got on his walkie-talkie or whatever and called someone to come over and check it out. And then a few minutes ago, someone came. They've now turned whatever is making the loud noise off. So hopefully they're going to get it repaired. I hope this doesn't affect temperatures in the classroom because it's going to be a pretty warm day today. But I think this morning we'll be fine. But that's why we're late getting started. All my great plans. Well, the other reason is I also wanted to check on something before I said anything, just to make sure my memory was right on it, and it is true. Next Tuesday, the 25th, okay, we have what they call planning hearings on the Birmingham campus at 10 o'clock in the morning. The math department does, and I'm the chair, so I have to be there. Well, if I were to have class here, we could only meet 8 to 9:30 at the very latest because it takes me about 30 minutes to get over there. Now, that's kind of pushing it because I'm planning to spend all my office hours today working on that. I planned to spend them last Tuesday. I was registering students and taking care of other things and didn't get much done on the planning hearing. Like I said, I came in early this morning, picked up the notebook and stuff like that, but I still couldn't get anything done because of this. I had planned last week to do it, but then they put me on the biology search committee, so I couldn't do it then. So it's down to today. Now, it depends on how much I can get done today and how much I can take home and work on it there over the weekend. And it may be that it'll be perfectly fine with me. If I'm ready and everything's ready to go, then I'll have class at 8 o'clock Tuesday morning, but we'll have to end by 9:30, maybe a little before that. And then we can make up the extra 30 minutes or so on Thursday if we need to. Or we can make it up today if you wanted to. So I was hoping there would be students here so we could talk about it. Since there aren't, what I would say to do is check your email and Blackboard before coming to class on Tuesday to see if I've left a message. It may be that I'll have to go straight to the Birmingham campus and get the last minute things together. I can't remember if all the instructors have sent me the data I requested. If they haven't, I may need to go there and chase people down and get it. I'm hoping that's not going to be the case, but if it is, then I will let you know we will not have class at all on Tuesday. But if everything's in order and ready to go, then I will we'll plan to have class Tuesday morning at 8 and end by 9:30 so I can get over to the Birmingham campus and get the hearing done. And that will mess up office hours on Tuesday too. I'll be over there from the hearing is 10 to 11. However, the next one coming up at 11, I need to be there for part of that too because we do some things together. It's biology natural science department, and we do some of the unit goals with them. So I maybe have to be there for no more than 30 minutes of their meeting. And the reason I say that is because I've got a 12 o'clock class, so I'm going to leave by 11:30 to get back over here. So basically, there's a whole 2 hours office hours, 10 till 12. I'll either be over there at the hearings or I'll be on the way back here, and then class starts at 12. Now, I should be back in the office for office hours 3:30 to 5:15 as usual on Tuesday. I'll be there today, Tuesday, and then Thursday should be normal office hours with no problems. So, just wanted to run that by people and let them know ahead of time. However, nobody's here to tell, but hopefully someone will listen to this. All right, that in mind, let's move on. Sorry, we're late getting started. We're in Chapter 4, Higher Order Differential Equations, Preliminary Theory 4.1, Linear Equations, and we're talking about, we're on Example 6 on page 124, linearly dependent set of functions. So here's a set of functions. Just let me get my pen activated. Okay. F1, first function, square root of x plus 5. 5 is outside the radical. F2, this function is square root of x plus 5x. F3 is x minus 1. F4 is x squared. Can't write. Okay. Eraser didn't pick up. Okay. All right. Now, it says it's linearly linearly dependent on the interval 0 to infinity. Okay. Why 0? Well, two of those functions have square roots in them, and you can't take the square root of a negative number. Marcus is here. I'm so glad. Okay. Sure, I'm on the right date here. Okay. I've already started the thing. I've said this on String Mathematics. It'll be on YouTube later. But let me run it by you now. Next Tuesday, they've skipped, wait a minute. I'm recording, but I can't project until I plug this in. I didn't need to project because no one was in here, but I didn't realize I hadn't done this yet. I turned on the projector, not realizing I'm not connected to the projector. Okay, yeah, there we go. Here's the deal. Next Tuesday at 10 o'clock in the morning, we've been scheduled for a planning hearing over on the Birmingham campus from 10 till 11. Well, obviously, I can't be there at 10 and have this class, end this class at 9:50. I don't drive that fast and wouldn't think of it. Okay. So, and that's next to the last day of class. So I've got a, next, say again? Monday the 31st. So that means we don't meet again after next Thursday. Okay. So here's the deal. I've gotten most of the data sent to me. I don't have it all printed off, and I don't have it put together and the analysis done. I had planned to do this, be working on this Tuesday, and every spare minute Tuesday, I was either registering students or helping a student do this or that, or with faculty members. I got 0 done during my office, well, not quite 0, but close to 0 done during my office hours. So, and the previous week I planned to do it, but they had me doing the screening and interviewing for the biology position. So this is my last day to have any time in the office to do anything with it. So basically during office hours today, that's what I'm focused on. Getting everything ready for that, much as I can. That'll be 10 to 12 today, and then again 3:30 to 5:15 today. If I can get everything that I need put together, or at least gathered together, I can take it home and put things together. Okay, and if that's the case, then we can meet here for class Tuesday morning, 8 o'clock. But I'll have to leave by 9:30 to be there by 10 o'clock. Okay? Now, and I haven't checked to see if everybody responded, if some of my instructors haven't responded or I don't have all the information I need, I might need to go over there early on Tuesday and get with them and get the documentation that I need from them. If that's the case, then I might need to just go straight to the Birmingham campus and not even come here to this campus. Now, with those two possibilities in mind, and I won't know until at the end of business today, basically, or even over the weekend. I think I'll know by end of business today. Do you want to plan to go in and have class at 8 o'clock, and then if I can't, I'll put it out there on Blackboard, and it'll send you an email as well. Or do you want to say, let's just not have class on Tuesday and double up the class on Thursday? Second? I can't hear. Okay. Well, we'll wait and see if Megan comes in and see if she has a preference too. I can go either way on that, but it's just that it's a very inconvenient time. I wanted them to schedule me for the afternoon on Tuesday, then it wouldn't mess with classes any. But of course they don't do it. Administrators really don't care about classes. They don't want to miss a wedding, miss lunch, miss a weekend, take a break when they want to. They don't really care about classes. So anyway, watch your email. Right now, let's plan to have class 8 o'clock Tuesday morning. Watch your email, and if I know that I can't be here, I will send that out and we'll double up on Tuesday. Okay? All right, we'll do that then. All right, we were doing example 6 on page 124, chapter 4, higher order differential equations. 4.1 is preliminary theory linear equations. And this was the setup. We have here a set of functions, f1, square root of x plus 5, f2, square root of x plus 5x, x3, x minus 1, and f4, x squared. And this is on the, say again? It's on page 124. I'm sorry? Yeah. Chapter 3 was modeling, I think it was. And what's that? We skipped chapter 3. Okay. Things have not gone as fast as I thought they would this summer. I thought we were doing really well in the class, except we missed Tuesday. I had to be in Louisiana because the vice president wanted to attend the wedding and didn't want to do the meeting we could have done in Atlanta on a Friday, Saturday. He wanted it on a Monday, Tuesday. Again, didn't care about classes. Then 4th of July was on a Tuesday, and so we've lost at least 1 week. Oh, and then I had my doctor's appointment. Well, we made that one up. So with 2. What's that? I can't hear. I didn't give it to you. That was test 1, wasn't it? Oh, wait. No, okay. Oh, you didn't get the test for chapter 2. Let's see. Okay. So, this is a set of 4 functions on that interval. Now, I was just mentioning, why is it on 0 to infinity? Well, you could have included 0, they didn't here. The main reason is, look at the first 2 of those functions have the square root of x in them. You can't have any negative numbers for x, so therefore none of the negative numbers could be included. You could have included 0, that would have been fine, but they didn't. They just did 0 to infinity, which is fine. So they're all defined there. But they say they're linearly dependent. Now, why would that be the case? Well, that means at least one of them can be written as a linear combination of the others. Okay? And just looking at these, this has a square root of x and a constant. This has the square root of x and a 5x. This one has an x and a constant. Well, just looking at that would suggest to me that F2 could be written as some linear combination of F1 and F3. Because you see the square root of x is there, the x is there, the constant's there. So I'm going to make a guess on that. So let's see if we could do that. Okay? Let's see if the square root of x plus 5x can be written as some combination A. Let's see, do they use, I think they use C's, so let me use C's. C1 times the square root of x plus 5 plus C2. Now this is just a guess. There's no guarantee this is going to work. Times x minus 1. Okay, there's the some linear combination of those 2. So this would then be C1 on the square root of x plus 5C1 plus C2x minus C2. Okay? Now, let's see if we can make that work. Let's combine these 2. Let's combine these 2. C1 square root of x plus C2x plus 5C1 minus C2. I put those together because those are constants, right? Now, what we have here, is that C1 would have to be 1, right? So let's write that down. C1 would have to be 1. Looking at the next, it looks like C2 would have to be 5. Wouldn't you agree? Okay. Now, this combination of these 2, 5C1, which would be 5 times 1, minus 5, there is no constant here. That had better be 0. Look at that. It is. 5 minus 5 is equal to 0. Yes. That linear combination of those 2 functions makes up that function. So therefore, this is a linearly dependent set. Now, if you left off F2, that would be a linearly independent set. And how can you see that? Well, this is the only function with the square root of x in it. You can't make a linear combination of those 2 and get a square root of x. They don't have one. This is the only one with an x in it. You can't make a linear combination of this one and that one and come up with an x. And then certainly, this is the only one with an x squared in it, so you can't do a linear combination of that and that to come up with an x squared. So, but you could, and we did, find the linear combination of the other 2, just 2 of the 3 functions that were left, to come up with a F2. Okay? So that was linearly dependent because you could come up with a linear combination of other functions in the set. Now, without all the C's being 0, okay, that will always work, but that's not really an option. The other C, by the way, the C for L4 would be 0. That's fine. let's move on to solutions of differential equations. Finally, we're primarily interested in linearly independent functions, or more to the point, linearly independent solutions of linear differential equations. Although we could always appeal directly to the definition we had before, it turns out that the question of whether the set of n solutions of a homogeneous linear nth-order differential equation is linearly independent can be settled somewhat mechanically by using a determinant. And you've had linear algebra, right? I can't recall if Megan has. Do you remember? I know she has it taken from me, but is she a Lawson student or is she a transient? She's a transient, so I don't know. She may have had it back on her campus. I don't know. So let's say that we have some functions. Let's clean the page here. Any questions on what we did on example 6? Okay. Clean the page here, and let's say we have a set of functions. f1 of x, f2 of x, f3 of x, dot, 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 all the way up to f sub n of x. So we have some set of n functions, okay? Suppose that each of those functions possesses at least n minus 1 derivatives. And all of these have n minus 1 derivatives, okay? If that's the case, then what you do, you set up this thing called W. And it's called a Wronskian. W-R-O-N-S-K-I-A-N. Has to be named up, yeah, there it is. Wronskian determinant was named after the Polish philosopher and mathematician Józef Maria Hony-Wronski. Okay. 1778 to 1853. If you think about that, that was just at, well, probably during our Revolutionary War, up until shortly before the war between the states. So that's when he developed this, while we're over here getting established as a nation. He was over there coming up with some pretty incredible mathematics, okay? And here's what the Wronskian is. The Wronskian is a function of those, is itself a function of functions, okay? F1, F2, F3, dot, 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 up to and including F sub n, okay? And here's what the Wronskian is. It's a determinant. Remember those? What you put in the first row is F1, F2, F3, dot, 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 up to F sub n. Okay? Second row is the first derivative of F1, first derivative of F2, first derivative of F3, dot, dot, dot. Let me get that cleaned up a little bit. Okay? Up to F, the first derivative of Fn. And the third row is, as you might guess, the second derivative of F1, the second derivative of F2, the second derivative of F3, dot, 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 up to the second derivative of F sub n. And that continues until you get to the n minus first derivative of F1, the n minus first derivative of F2, the n minus first derivative of F3, dot, 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 up to the n minus first derivative of F sub n. Okay? All these are dot, dots. Everywhere a dot, dot. Okay. So, we have n columns and n rows, because the function itself, the first derivative, second derivative, third derivative, so you can always have one more row than you have derivatives. So that's why when you get to n minus 1 derivatives, that would be that many derivatives plus the function itself. So you have n rows, n columns. Okay, now what you do is take the determinant of that. Okay, quiz on your linear algebra now. If those are not independent functions, what's the determinant? Okay? If any one of those columns or rows or columns, okay, is a linear combination of the others, then your determinant winds up being 0. Okay? Because if you can do row reduction and stuff like this and wind up with a row of 0 somewhere, your determinant's 0. So, take the Wronskian, and that's called the determinant. Okay? That's just a definition. What you do with it. That's where theorem 4.1.3 comes into play. Okay? So I'm going to clear that, and let's imagine that we have y1, y2, y3, ... up to, are they still using n? Yeah, y sub n. Let those y's there be solutions of the homogeneous linear nth order differential equation that we've been talking about for a while here, on some interval I. Then the set of these solutions is linearly independent on that I, if and only if that Wronskian we just had up there is not equal to 0 for every x in the interval. Okay? So, if there were some x's that made that 0, but if you can exclude those and no others make it 0, then it can be linear on some interval that doesn't include an x that would make that 0. Okay? Now, that's the theorem. It follows from this that when y1, y2, y3 up to y sub n are in solutions of your differential equation on some interval I, the Wronskian is either identically 0 or never 0 on the interval. Okay? Thus, if we can show that the Wronskian for those functions is not equal to 0 for some x0 in I, then the solutions y1 through yn are linearly independent on I. For example, here are two functions. Okay? y1 of x is equal to the cosine of 2 log n, if I could write, log x, sorry, I can't even talk, okay, over x cubed. There's one function. Here's a second function. y2 of x is equal to sine of 2 log x over x cubed. Okay? It says these two are solutions for this differential equation. X squared y double prime plus 7x y prime plus 13y is equal to 0. Okay? They claim, and this is on the interval 0 to infinity. Now let's say y 0 to infinity. Okay? Well, there's nothing here that would indicate there's a problem. But if those are solutions, guess what? Log x, you cannot take the log of either 0 or negative numbers. So therefore, you would have to have this. No option over here whether that can include 0. No, it can't. You can't take the log of 0, but at least, and you can't divide by 0, okay? So at least everything else there defined, still not clear whether that's the case or not, okay? Now, I hate to do this, but it's a good practice. Are they telling the truth here? Okay. Are those indeed solutions to this? Let's verify. Unfortunately, this is going to take a little bit. What do we need to do first? take a derivative. Y1 prime is equal to, oh man, what a quotient rule, right? So let's do it. That's low x cubed d high, which would be minus sine of 2 log x times chain rule 2 over x. That's the numerator, the derivative of the numerator, minus high, that's cosine of 2 log x over x cubed. Wait a minute, yeah. No, numerator, don't do the x cubed. Second, where did that come from? Okay, so that's numerator times the root of the denominator, which would be a 2x squared. Right? No, I'm sorry, 3x squared. Not right. This is right. Okay. Right? Okay. All over x cubed. No, x to the 6. X squared squared. I mean, x cubed squared, which is x to the 6. All right. Now, that is such a mess. Okay. Let's see if we can clean that up a little bit. What I'm going to do is multiply the numerator and the denominator by x. Every term in numerator and denominator by x. And by the way, no, I'm not going to do that because I just saw I left off parentheses. Okay. This is times that. Okay. It's the top times the derivative of the bottom. And I put the minus on there as if you're subtracting. The minus is part of the derivative. Okay. Now we see this x can go away. Okay. So what we have, cleaning that up a little bit, is a minus 2 sine, now let's see, let me gather a few more terms together, minus 2x squared sine of 2 log x minus 3x squared cosine of 2 log x. By that, over x to the 6. Yeah. X to the 6. But you have an x squared term, an x squared term there, so this makes that an x to the 4th. So let me clean that up a little bit. Okay. Now I think we're okay. All right. There's your first derivative. Told you this was a pain in the neck. Let's do the second derivative. I don't have room. y1 double prime is going to be, you got to do the same thing, except now you got even a bigger mess. Okay, low d high, so that would be, low is x to the 4th, derivative of the numerator is, I see there's going to be, it's going to be a minus 4, the 2 that's there and the 2 we're going to get when we do the chain rule. Okay, cosine of 2 log x, okay, and then times the derivative, we already did the 2, and divide by x, so this will make this a 3. And again, gotten sloppy, those are multiplied by each other. Low times derivative of high, okay? So your minus sign stays, okay? That's the first one. Let's continue. That low, which is x to the fourth. I probably shouldn't have wiped that out yet. Minus 6. Okay. No, it's going to be a plus, isn't it? Because when you take the derivative of cosine, there'll be a minus sign, so it changes that to a plus. 6, yeah, we're going to be okay. Okay. You still have the, I didn't write it in the right place, but x to the fourth, that's still the low times the second term here. Plus 6, x to the fourth from the low part. Derivative of cosine is sine, or minus sine, so that's what changed the sign. Sine of 2 log x. And then you have, I already did the 2, and you have over x, so that becomes an x cubed 2. So there's your low d high. Now you've got to do a minus high d low. Well, both of these are plus in here, so that's going to turn out plus, and the derivative of low is 4x cubed. So this first one is going to be plus 8x cubed sine 2 log x, and then the second term will be a plus, and you got a 4 times 3, so that's going to be a 12x cubed cosine 2 log x. All right, there's your numerator. Your denominator is over x to the 8th. Sorry about the cramped room over here. But you have an x cubed here, an x cubed there, an x cubed here, and an x cubed there. So this brings it down to x to the 5th down there, right? Okay. Why did I do this? Okay. So what that y double prime is going to wind up being, let's see if I can get it written in here. Y1 double prime is going to be equal to minus 4 cosine 2 log x plus 6 sine 2 log x plus 8 sine, well, wait, let's combine like terms. That'll make it so much easier. 8 and 6 is 14. Okay. Wow, that does make it much nicer. That would be a 14 here, and you had a 12 cosine and a minus 4 cosine, so that'll be a plus 8. Okay, all over x to the 5th. Except this is a minus. No, that's a plus. Okay, good deal. All right. Now let's plug in and see what we get. When you do an x squared times this, basically that'll leave an x cubed in the denominator. So this will be an 8 cosine 2 log x over x cubed plus 14 sine of 2 log x, okay, over x cubed, okay. All right. So this will be an x cubed here when you do x squared times that thing, okay? Plus 7x times y prime. Well, here's your y prime, and it's plus 7 times this, so that will be a plus, I'm sorry, okay, sorry it's so crowded here. It's plus 7x times x. Well, the x is going to wipe that out and make it an x cubed also. So we're going to be fine. So you got a plus 7 times a minus 2. So that's going to be a minus 14 sine 2 log x. And then you're going to have a plus 7 times a minus 3 is a minus 21 cosine 2 log x. And that's going to be over x cubed. Okay? Then we have a plus 13 times your y. y1. So that's going to be plus 13 times cosine of 2 log x. All right? Over x cubed, because that's part of your y cubed. So all your x cubes, everything's fine, so all we have to do is combine numerators. Here's a plus 8, a minus 21, and a plus 18. 8 plus 13, I said 18, 13. 8 plus 13 is 21, so those add to 0, and plus 14 minus 14, everything's over x cubed. They add to 0. Sure enough, that one works. Okay? Can we say, we'll take the word that the sine one does too, the y2. You'd have to go through the whole thing, but it's going to work. Okay? So, we have verified that those two functions are solutions for that. They didn't tell us to. Okay? But we did. It says, note that the coefficient functions of a2 is equal to x squared, a1 is 7x, and a0 is 13, are continuous on 0 to infinity. a2 is not equal to 0 for every value in x in the thing. So therefore, we can do the Wronskian. Okay? So notice what they were saying. Your coefficient functions, nothing messes up there. Okay? So let's look at the Wronskian. Now, I'm going to try to be very selective in what I erase. Okay? All right, I'm going to erase this. That's no sweat. Okay? I'm going to keep my y1 and y2. Oh, I lost some of my y1. Okay. All right. I think I'm going to lose this. What's that? Okay. All right. I do want to hang on to y1 prime. So here it is down here. Okay, that's your y1 prime. And there's your y1 double prime. And the rest of this, I think I can lose. Only thing I haven't done, I don't need the y1 double prime. All I need is up to y1 prime. So I don't even need this one, so I'll lose this one too. So all I need to do, I'm just going to bring this down. That's y1 prime down here. Okay. I need to do my y2 prime of x. I didn't do it, but let's do it now. As we said before, that's going to be low x cubed d high, which is going to be times a minus 2 cosine of 2 log x times 1 over x. I already did the 2 there, so that's going to make that x squared. Okay? Minus high d low, which is going to be a 3. It's going to wind up being a, okay. Let's just take it. 3x squared times derivative of that, times this, times sine of 2x, 2 log x, okay? Okay. Over x sixth, but then the x squareds will go out and make this an x fourth. So what we have is y2 prime is equal to a minus 2 cosine 2 log x minus 3 times the sine of 2 log x over x fourth. Okay, so there's your y primes, or y1 and y2. Okay, notice the similarities. Very, very similar there. Okay, not the same, but similar. So we do the Wronskian. Okay, and the Wronskian of this is going to take more room than I can write down, I think. The Wronskian of y1, y2, okay, is equal to the determinant of y1, which is cosine of 2 log x over x cubed. I'm going to do y1 prime underneath that, and that would be minus 2 sine of 2 log x minus 3 cosine of 2 log x over x fourth. Okay? Now, I've got to erase something here, so I'm hoping it's not going to come back and bite me. Okay, this line here we've already taken care of. Okay, and the y2 prime is going to go right down there, so I'm going to just take this yuck. Take that out of there, okay, and then put in this, sine of 2 log x over x cubed. Okay, that's the Wronskian, the determinant of that. Okay, I think I've got everything in place. So I'm going to erase this. I've already gotten it written down. I don't need it again, I hope. I've got it there. So let's do that determinant. Okay. It will be this times that. All right. When I multiply those two together, that's going to give me a minus 2 cosine squared of 2 log x. Okay? minus 3 times sine of 2 log x times cosine of 2 log x. Okay, now that's multiplying our numerators together. Multiplying the denominator together give you x to the 7th. Okay, minus this one. Well, notice this is all going to be minus, so that's going to give you a plus. And you do those products, and you get 2 sine squared of 2 log x plus, well, yeah, it'll be a plus there too. 3 let's see, sine 2 log x cosine 2 log x. Okay, over x to the 4th, not 7th. Okay, 4 times 3 is 7. Okay, 4 plus 3 is 7. Okay. Now, I think you see, I hope you see, we can combine everything over x to the 7th, so that's common denominator. When you combine these two terms, that basically is going to give you, no it isn't. Okay, sorry about that. I was going to say 2, but it doesn't. Because one's a plus and one's a minus. Okay. It looks more like a cosine two times the cosine of 4 log x. Okay. Oh my goodness gracious. Says rather than expanding this unwieldy determinant, which I was starting to do, we choose x equal 1 in the interval and see what that comes up with. Okay. Now why can they do that? What they said before, it follows that if it's either identically 0 or never 0. So if you pick any one value, if that one value is not 0, it'll never be 0. If that one value is 0, all the others would be 2. So sounds like cheating to me, but they're doing it, and I think I'm all in favor. So rather than doing what I was starting to do here, I thought there was going to be some things that came out easily, and I was mistaken. Badly, but let's just do one of those, x equal 1. Okay, it's about as simple as you can get on the interval. X can't be 0, so you can't use that one. So let's do the Wronskian of y1 of 1, y2 of 1. Okay, and that will be cosine of the log of 1 is 0. 2 times 0 is 0. Cosine 0 is 1 over 1. So that's going to be a 1 there. Sine of 0, because the log of 1 is 0. So sine of 0 is 0. Okay? Denominator. Log of 1 is 0. Sine of 0 is 0. That goes away. Over here, log of 1 is 0, so that's 0. Cosine of 0 is 1, so that's going to be a minus 3 over 1. Okay? Over here, it's going to be a minus 2, because log of 1 is 0, cosine of 0 is 1, times negative 2 is that, and this one goes to 0, that's over 1. Okay, so there's your determinant. Okay, now take that determinant and you get a -2 plus 0. Okay, how did I get a -2 there? Okay, I get a +2 here rather than a -2. I've already erased all my stuff, so I can't go back and check. Yeah. And I think they're probably right, because when you take the derivative of the derivative of sine is positive cosine, so not negative. Sorry about that. So you do get a +2. That's not 0, and the fact that it's not 0 is sufficient to conclude that none of your y1s and y2 would produce a Wronskian of 0. Okay? Now, I need to take a quick break, a bladder break. Sorry about this. I hadn't intended to, but let me... All right, I'm back. My students aren't back, but I'm back. One got a phone, had to go out and take it. I noticed he took his books with him when he went, so I was suspicious if he was going to come back, and he hasn't. So let's move on. A set of n linearly independent solutions of a homogeneous linear nth order differential equation is given a special name. It's called a fundamental set of solutions. I'm not going to write this down because I think both of you have your books. Any set, y1, y2, y3, up to yn, of n linearly independent solutions of a homogeneous linear nth order differential equation, as in equation 6, which you'll find back on page, we've been going at it for a while, page 121, under 4.1.2, that basic homogeneous differential equation. Okay? On some interval I is said to be a fundamental set of solutions for the equation. The basic question of whether a fundamental set of solutions exists for a linear equation is answered in the next theorem, and here it is. There exists a fundamental set of solutions for the homogeneous linear nth order differential equation that's listed in 6 on page 121 on an interval I. Okay? There does exist one, and if you can find it, you got it. Okay? Now, analogous to the fact that any vector in 3 dimensions can be expressed as a linear combination of the linearly independent vectors I, j, and k, then any solution of an nth order homogeneous linear differential equation on some interval I can be expressed as a linear combination of those linearly independent solutions on I. In other words, the n linearly independent solutions, y1, y2, y3, up to yn, are the building blocks for the general solution of the equation. Okay? Leading to the next theorem, that y1, y2, y3, up to yn be a fundamental set of solutions of the homogeneous linearly nth order differential equation 6, way back there, 121 I think it was, then the general solution of the equation on the interval is some linear combination of that fundamental set. Okay? So y would be some linear combination c1 y1 of x plus c2 y2 of x plus c3 y3 of x all the way up to cn yn of x, where c sub I, where the i's going from 1 to n, are arbitrary constants. Okay? Now, that theorem states that if you come up with a set of functions, if y of x is a solution of that differential equation on the interval, then the constant c1, c2, c3 can always be found so that that y of x that you knew was a solution is some linear combination of the fundamental set. And they proceed to prove that for n equal 2, basically doing your Wronskian. And, well, it's not really a Wronskian there. They just do a determinant of your coefficients and go from there. Let's move on to example 7 and see what we can do with that. All right. Here are some functions. y1 is equal to e to the 3x. y2 is equal to e to the minus 3x. Okay? Pretty ugly 3s there, aren't they? And they claim these are both solutions of the homogeneous linear equation y double prime minus 9y equals 0 on the interval minus infinity to infinity. No restrictions anywhere. Okay? Now, I hate to take the time to do it, but let's do it. Let's verify this. What we have to do is find y1 prime, and that would be 3e to the 3x, and y1 double prime would be 9e to the 3x. Okay? You can see plugging that in, 9e to the 3x minus 9 times e to the 3x, sure enough, that's 0. Let's do it for y2. y2 prime is equal to minus 3e to the minus 3x, and y2 double prime is equal to positive 9e to the minus 3x. Plugging that in, 9e to the minus 3x minus 9 e to the minus 3x, sure enough, is 0 everywhere. Okay? So yeah, those are two solutions. Now, Brooks' issue, are they linearly independent? Yes, they are. Okay? So therefore, they're solutions to a second order differential equation. Therefore, they're a fundamental set. Okay? By inspection, the solutions are linear independent. We can do it by the Wronskian as well. And since we've already done everything we could, let's do the Wronskian for this y1 and y2. And that would be the determinant of e to the 3x, e to the minus 3x, 3e to the 3x, minus 3e to the minus 3x, and do a cross multiplication here, and you get minus 3, because e to the 3x times e to the minus 3x would be 1, okay, minus 3, and that's equal to minus 6. Not 0, so therefore you do have a linearly independent set, okay, for every x in there. We conclude that y1 and y2 form a fundamental set, as we already said. So consequently, you can write your general solution, and that's what we call it, is y is equal to c1 e to the 3x plus c2 e to the minus 3x. Some linear combination of those two. Everything that is a solution for that. All right. Let's move to example 8. Now that's a hyperbolic and sine and it says that y is equal to 4 hyperbolic sine of 3x minus 5e to the 3x is a solution of that differential equation as well. They say verify it. And then they want you to obtain that solution from the general solution. Now, frankly, when I'm messing with hyperbolic, I just as soon change them to exponentials because otherwise I tend to make mistakes, or I have to look up and see and make sure I'm getting the right derivatives and things like this. So rather than do that, I'm just going to skip that problem. Work on it yourself, especially if you feel like you'll need that in the future. If you can't get it, I'll be glad to answer any questions you have on it. Okay, let's move on to example 9. Here are some functions. y1 is equal to e to the x. y2 is equal to e to the 2x. y3 is equal to e to the 3x. They tell us they satisfy the third order differential equation y triple prime minus 6y double prime plus 11y prime minus 6y is equal to 0. All right? Now, let's see if we can do a real quick job of verifying that. Y1 prime is e to the x, and y1 double prime is equal to e to the x, and y1 triple prime is equal to e to the x. That one was easy. Okay? y2 prime is equal to 2e to the 2x. y2 double prime is equal to 4e to the 2x, and y2 triple prime is equal to 8e to the 2x. All right, do the same for y3. y3 prime equal to 3e to the 3x. y3 double prime is equal to 9e to the 3x. And y3 triple prime is equal to 27e to the 3x. All right. Let's evaluate each of those. Y triple prime, let's do number 1 first. Minus 6 times that, so that would be 1 minus 6 is minus 5, plus 11, that would be plus 6, minus 6 is 0. That one was easy. Okay? This one will be 8. All these have e to the 2x's on them, so I'm not even going to say that anymore. So this will be 8 minus 24 will be minus 16. Yeah. Plus 22 will be plus 6, minus 6 is 0. That works. Okay, the next one, every term's going to have e to the 3x in them, so I'm just going to factor that out and kind of ignore it. Y triple prime is 27, minus 54 is minus 27, plus 33 is plus 6, minus 6 is 0. Okay. All of those do check. Okay? Man. So those three are solutions. They satisfy that differential equation. Now we got to see, are they linearly independent? And that's where the Wronskian comes in. So the Wronskian of these three, e to the x, e to the 2x, e to the 3x, would be the functions across the top, e to the x, e to the x, e to the 2x, e to the 3x. Okay? First root is in the next row, and that would be e to the x, 2e to the 2x, three e to the 3x. Okay? And then your second derivative, which as far as you have to do, is e to the x, 4e to the 2x, 9e to the 3x. I'm sorry, wrote that poorly. I'm having trouble breathing, so yesterday I was, and I think some on Tuesday too, mostly yesterday, I was having enormous problems with my eyes. And I don't know what was going on, and it was a real pain. But anyway, let's do the determinant. I don't know if you remember the sort of the easy way to do determinant of a 3 by 3. Basically repeat the first two columns after that third column. And I don't have room to write them there, but let's mentally do that. So then you go down this way, and that will be 18 e to the 6x. Okay? And if you wrote this column again, that would be plus, it would be these two times that one. And that would be 6 e to the 6x. And then this one times those two, and that would be plus 4 e to the 6x. Then you subtract the down ones, okay? And that will be a minus 2e to the 6x. Okay, the next down one would be this one and those, whoops. Okay. This one and those two, and that would be a minus 12 e to the 6x. And then the last downer would be these two and that one, and that would be uh, 9 e to the 6x. Okay. This at 18. I don't know why I wrote 19. I'm multiplying. Bizarre. Okay. All of them are e to the 6x's, so let's just add the coefficients. And by the way, this is a minus here. Again, the brain's not working well this morning. Okay. So your positives will be 28. And your negatives are going to be 9 negative 23, and this comes up being 5e to the 20, e to the 6x, okay? Now, they got 2, I've got 5. 28, and there you have 21, and 2 is 23. So I did something dumb here. Let's do our minuses again. That would be 2 minus 2e to the 6x minus 12e to the 6x minus 9. Ha! That's 18. I missed that 2 there. Alright. So this 18 and that 18 go out. And this gives you a 10 minus 14. That's a minus 2. They got a plus 2. Yuck. I don't want to waste a lot of time with this. We got a 18 plus 18 there. I say only a plus 3 there. How did I mess that up? And then you got a plus 4. That makes it even worse. Let's go the other way. And you got a minus this first one here is a minus 12. I did that second. Let's do a minus 12 first. Then you get a minus 9. And then you get a minus 2. Okay, I did it in a different order. Okay? So I don't see the 18 in there at all. Okay. Now let's see what we got. I didn't think this was going to be this complicated. It really isn't. I just patched it up. Let's start over. Okay. All right. 18 plus 3 plus 4 minus 12 minus 9 minus 2. All right, let's start over with those. All right, this adds to 22, 25. Okay, minus 14 and 9 is 23. Yeah. How in the world did I mess that up? 2e to the 6, which is not 0 and never will be. Okay. So this shows they are linearly independent. So our overall solution, general solution, is y is equal to some C1 e to the x plus some c2 e to the 2x plus some c3 e to the 3x. All right, that took way too long. All right, let's move. Well, I've got to go get something to drink. My throat is so dry and sore, so I'm going to pause this for just a moment. All right, now we move on to non-homogeneous equations. We've got down pretty much, I hope, all the tools we need for homogeneous. Any function y sub p, free of any arbitrary parameters, okay, that satisfies, and this will be the equation 7, which is back on 121. That's the one just like the homogeneous case, except you have a g of x on the right-hand side, with homogeneous has a 0 on the right-hand side. Okay, so that's your non-homogeneous case. So any function y of p free of arbitrary parameters that satisfies that equation is said to be a particular solution of the equation. For example, it is a straightforward task to show that for the constant function yp is equal to 3 is a particular solution for the non-homogeneous case equation y double prime plus 9y is equal to 27. They say it's a straightforward task to show that, okay? Let's clear the ink here, and let's see what they're talking about. Y double prime plus 9y is equal to 27. Okay? Well, they said for a particular solution yp equal 3, it says that's straightforward to show that is a particular solution for that equation. Well, what does it mean? Well, if yp is equal to 3, yp prime is equal to 0, as is yp double prime. Okay, that's legal, it's fine. And if you plug that in here, you get that 0 plus 9 times 3 is 27. Yeah, okay. That is a particular solution, has no parameters in it. It just happens to work for that situation. Most of the time, they're not that easy or simple, okay? Now, if you have a bunch of other y's, y1, y2, y3, up to yk, and they're solutions for the homogeneous case on some interval I, and yp is a particular solution of 7 on that same interval, then you just take your general solution to be the y is equal to the c1 y1 plus, and I probably should put the of x there, plus c2 y2 of x plus c3 y, yuck, parentheses in the wrong place, get the writing too fast, y3 of x plus dot 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 plus c, I think they use I now, k now, okay, why they changed the subscripts, I don't know, yk of x, okay, that is your general solution for your homogeneous case, okay, but if you have some other function, a particular solution that makes it true for the non-homogeneous case, then just take this and add that yp of x to it, and now you have the solution for the non-homogeneous equation. If you think about it, it makes sense because the linear combinations of the others will add to 0, and then the yp will make the remaining thing true, okay? Now, they introduce the concept of the operator. L is a sub n, d sub n plus a sub n minus 1, d to the n minus 1, plus all the way up to a1, d plus a0, whereas yp is transformed into g of x, if we use k equal n linearly independent solutions of the nth order homogeneous equation, 6 back there, then the expression in 10 becomes a general equation solution for 7, which is your non-homogeneous case. So here's the theorem that supports this. I guess probably I ought to write it down. Let y sub p be any particular solution of the non-homogeneous linear nth order differential equation. Okay, that was your equation 7 back on 121. Okay, on the interval I, and let your y1, y2, y3, all the way up to and including, this time they use yn, be the fundamental set of solutions, a fundamental set of solutions of the associated homogeneous equation 6 on I, then the general solution, like we just said, would be c1y1 of x, just the same thing I've got up here. Okay, it's just that written again, only now it's n rather than, I don't know why they went from k to n. Okay, doesn't matter. And just add your thing in there. They do a little proof on it. It's really not that difficult of a proof. If you want to look at it and see and follow, probably be pretty good. Now, another new term here, and that's a term that's called a complementary function. We see in Theorem 416, the one we just talked about there, that the general solution of the non-homogeneous linear equation consists of the sum of two functions, your homogeneous one and your particular one. Okay? The homogeneous solution here we'll call the complementary function. Okay? So that would be, it's called the general solution if that was equal to 0. If it's not equal to 0, but you set it equal to 0, it's no longer general, it's now called complementary. Then you find your yp, add that to it, and that becomes the general solution of your non-homogeneous case. Okay? It's just shifting the words a little bit. Okay? And that'll make it happen. Now, unfortunately, we've run out of time before we ran out of term, section. So we will begin next time. And I just don't know when next time will be. Okay? And again, I'll say it, I said it at the beginning, I'll say it again now. I've got that meeting required to be there at 10 o'clock on Tuesday. So, best case situation would be I'll come and have class here until 9:30, then go over there for the meeting. That's if I can get everything done today that I need done today and finish up over the weekend, and so I don't have to go over there first thing Tuesday. See, the trouble is Mondays are completely shot. I have classes here from 8 o'clock in the morning till 9 o'clock at night with 2 20-minute breaks and 2 10-minute breaks, and that's all. That's all, okay? So therefore, I have to get everything that I can done today and be able to work all the rest of it over the weekend at home, and then teach the class here on Tuesday morning. So Monday, I'm completely in class. So if I can do that, I'll be here Tuesday morning. If I can't get everything done I need done, and the main scenario here was either I don't have time to get everything put together here today for me to finish over the weekend, Or, as I'm putting things together, I found some gaps that people haven't sent me the things they had said they were going to, and I have to go over there and put those together on Tuesday morning. So I'm hoping that's not going to happen. I'm hoping I will have time to get everything I need done today, and then I'll be here Tuesday morning, have class from 8 to 9:30, leave to go to the Birmingham campus, get the meeting done, come back here, and then the rest of the week will be normal, hopefully. Okay? So, either we'll meet Tuesday morning at 8, or we'll meet Thursday morning at 8 and try to have a double class then. So, watch your emails and your Blackboard. Okay? I'll put the announcement on Blackboard if I'm not going to be here Tuesday morning. If you don't see anything on Blackboard, don't get an email. Be here Tuesday. I will be here, and we'll have class for an hour and a half. I'm hoping that's going to be the situation, but if not, we can live without it. Okay? So, I'll end it for